Good morning, everyone, and welcome to today's webinar on verification, more so electrical safety tester verification. My name is Syed Abidi, and I will be presenting this webinar today. Also joining us on the panel today is Dwayne Davis, who will be answering any questions that you might have, and Jim Kenzie, who will be hosting this webinar. We do have an Q&A utility available for you to ask any questions concerning the material being presented. And if you have any issues or questions related to running of the meeting, any technical support with audio and visual, you can address it directly to the host, Jim Kenzie, through the chat line. This webinar is being recorded and will be available to you on our website in a week's time. If you would like to get a copy of the presentation for this webinar, please contact Jim Kenzie. You can see the email address on the screen right now, jimk@asresearch.com. Okay, it looks like we're all set to begin and get into the main content of this webinar. So here's a brief outline of what we will be going over today. We're going to start with what is a verification test and why is it required. We're going to get into some examples from the IEC 60601 standard and a few other standards. Then we're going to briefly go over some of the basic electrical safety tests, and also we're going to get into details of how to verify those tests. We're going to give some examples, and then in the end we'll have a small little amount of time left for question and answers. Okay, having said that, let's jump directly into what we're going to be learning today in this webinar. So what is a verification test? Well, as the word implies, it is a procedure to ensure that a safety device or tester will properly detect product or device under test failures. So basically, verification of electrical safety testing equipment is a procedure which is often overlooked by manufacturers. Running test verification is very crucial to ensuring that a safety device will properly detect product failures. Now, while the task of setting up a test verification can seem to be daunting, it's a simple matter of having the necessary equipment and procedures in place so that the process is easy to follow. We know that an electrical safety test is as good as the tester itself. If the tester is defective, it will lead to inaccurate safety tests, which in turn can lead to bigger issues like electrical shocks and other safety hazards for the user. It is also, verification is also required by agencies, standard agencies such as UL, IEC, and TUV. And if you really think about it, it is an initial time investment upfront, but it pays off greatly by avoiding bigger issues and problems in the long run. So that is why verification of electrical safety test equipment is very important. According to UL, they have a document which is specifically, which outlines the importance of maintaining and verifying measurement equipment, which includes, of course, electrical safety testers. And this is a direct excerpt from the UL document which says that inspection and measuring and test equipment used to verify compliance with UL requirements shall be checked daily by the customer to ensure it is functioning properly. If this equipment is not used daily, then this function verification should be performed prior to use. Now, this shows us how important it is and how much importance is given to the safety tester verification by the standard governing agencies like UL. And performing electrical safety tests is done to ensure that basically an electronic product does not pose a shock hazard to the end user. An electrical safety test, however, is, as we saw, is only as good as the tester being utilized on the product. So, and due to the nature of electrical safety tests, it is very important to ensure that the tester itself is working and is in good condition, is detecting true failures and true passes. And due to the nature of manufacturing environments where these electrical safety testers are being utilized, they can get damaged internally without showing any physical signs of a problem. As a result, these damaged units can give incorrect readings with regards to insulation resistance, leakage currents, and withstand potential. Therefore, performing regular verifications on electrical safety testing equipment ensures proper operation and testing to agency standards. Also, environmental conditions like heat and humidity can affect the instrument's readings and accuracy over time, and it is possible to get false passes or failures on the device that is being tested. So this is why safety tester verification is being given so much importance, and rightly so. Well, I know we've been going over the basic electrical safety test in our previous webinar, for some of the previous webinars in the 2013 series of webinars. But it is always nice to go over. Not in this time. What we're going to do is we're not going to go over in too much detail what these tests are. We will still go over the basics just as a refresher for you guys, what these tests were and are, and then we're going to jump into some techniques of verifying these tests. But before that, let's just go over the 4 common electrical safety tests: ground bond and ground continuity, dielectric withstand test, also known as Hipot test, insulation resistance, and line leakage test. Before we jump into those tests, it is important to know that electrical safety compliance analyzers of today are very modern testers. For example, the Associated Research's Omnia 2 is a complete electrical safety compliance analyzer, and nowadays, due to the various functions of the units, it is very important to determine if the tester will fail properly when a regulated test value has been exceeded, or in a high volume production line setting, it can be easy to miss a unit that should have failed due to a bad tester. So therefore, performing verification on all unit functions ensures that a test unit is operating within the specified parameters. And also, according to UL procedures, if the test unit is taking measurements to make a determination on electrical safety, then it must be verified. Okay, just a reminder for you guys, if you have any questions regarding the material that is being presented, please feel free to use our Q&A facility. Okay. Next, we're gonna briefly look at some efficient verification processes and devices that can be used to verify if an electrical safety tester is performing within specs. Basically, as we know, electrical safety tests are designed to identify faulty insulation, improper grounding, loose connections, defective parts, unguarded light part, and excessive leakage currents. Therefore, simply shorting or creating an open between test leads can prove to be an efficient method of ensuring the base failure detectors on an instrument are operating normally. However, such methods cannot catch all the potential issues with the unit. Therefore, having a simple resistive network and relays, network of resistors and relays, can actually provide an easy means for an operator to check the functionality of the unit by just dropping potential across these resistive networks and setting limits such that the verification tests would fail. Additionally, building such a network with easily accessible parts and programmable control allows a verification to be run automatically with each verification process, makes running the verification test much easier, and providing the operators and technicians with a simple means of verification basically increases the chances that any problem with equipment measurement will be caught prior to product testing. One such method of, or one such device that can be used, that is very efficient in use for verification processes, is the TVB2 test verification box by Associated Research, shown in the picture in the bottom of this page. What this box essentially is that it consists of a series of resistors designed to draw a specific amount of leakage current. What this does is that each test type, if you note on the box, each test type contains two posts. One post is for a pass and one is for a fail. For example, here we're looking at the voltage withstand portion of the test box, and there's one pass terminal and a fail terminal. Basically, what's being done here is separate resistance values from each post is being connected back to the return post on the box, just to form a network of resistors for verification. And like I said, this test box uses and we're using this test box just as an example. Could be a different configuration of resistors and relays, but here we're going to use the TVB2 as an example for this particular webinar. Also, this test box can be used with most of Associated Research safety testers. If you look at this table on the page, it's basically giving us all the resistance values and test settings for different tests, AC withstand, DC withstand, insulation resistance, ground continuity, and ground bond. And you can see there's a pass-fail condition and instrument setting, and the ramp times are also provided in this table. So what we're going to do is, once we get into the verification of different test types, we will be using this table and the values and settings in this table as an example. Okay. So before we get into the verification, what we're gonna do is actually we're gonna go over all the basic electrical safety tests that I mentioned earlier, and right after reviewing what that test does, we're going to jump into how that particular test can be verified. So we're going to start with the dielectric withstand test. Well, as we all know, it is also known as Hipot test, which comes from the word high potential test. And this test is designed to stress the insulation of the device under test far beyond what it would encounter during normal use. The logic behind running such a test is that if the device can handle the force of a very high potential for a short duration, it should be able to operate at rated voltage without posing a shock hazard to the user. A Hipot test is basically a very versatile electrical safety test. That is because not only is this test designed to find the weak points in the insulation, it can also be used to measure excessively high leakage current, workmanship defects such as pinholes and scrapes, improper spacing with respect to a grounding point, and degradation due to environmental conditions. And the fact that this test is such a versatile test and it can detect a number of insulation failures, this test is generally specified by standard agencies as 100% production line test, production line safety test. Now, how this test is run is basically it involves applying high voltage across the current carrying conductors. Basically, by you can short line in neutral or plus and minus, and with a return point on a conductive chassis of the device under test. The Hipot tester will measure the resulting leakage current flowing through the insulation. The potential that is used in a Hipot test varies from one standard to another, but a common Hipot voltage formula is to take 2 times the rated voltage of the product plus 1,000 volts. Okay, so now that we have reviewed what dielectric withstand test is, and I'm sure we went in the previous few webinars, if we did go in a lot of detail about the dielectric withstand test, and we gave many different examples, and we also went over the circuits for all the electrical safety tests that we are going to cover here. So, like I said, we're not going to go into too much detail, but we will still review what each test type is and then how it's verified. So, how do we verify the dielectric withstand? Whether the dielectric withstand test is measuring the leakage current accurately and within specs. Well, in when the Hipot test what we're going to do is, again, we're going to use the example of the TVB2 box resistance values and test settings that we showed earlier in that table. So, using that same table and the TVB2 box as an example, the Hipot test voltage for a particular Hipot test is, say, 1240 volts. If you refer to that table, the failed circuit includes a resistance of 120,000 ohms or 120k ohms, and the passed circuit utilizes a 2 mega ohm resistor. The Hipot unit would then be set for two separate tests. The first would be a pass test. Basically, the Hipot unit will be set to output a voltage of 1240 volts AC. We can set based on that table again, we can set the high limit on the tester at 10 milliamps with a 2-second ramp up time and a 1-second dwell time. Okay. The high voltage lead from the Hipot unit will connect to the pass terminal on the AC withstand portion of the TVB2 box. If you guys remember, we saw there's a pass and a fail terminal for each of the 4 test types that are located on the TVB2 box. So here, for a pass test, for the ACW pass test, we're going to connect the high voltage lead from the Hipot unit to the pass terminal on the ACW portion of the TVB2 box, and the return lead will be connected to the return terminal of the TVB2 box, going back into the tester, Hipot tester. And then, using a simple Ohm's law calculation, we can determine that the leakage current should be around 620 microamps. Therefore, once we run this test using the tester, and if the tester measures a leakage which is close to 620 microamps, then this should result in a test pass. Well, similarly, the next test would be a fail test with the Hipot unit set to the same parameters as the pass test. The only difference here would be that on the fail side, the TVB2 box is utilizing a different resistor, which is the 120k ohm resistor. So similarly, leaving all the other parameters the same as for the pass test, what we're going to do is we're going to connect the high voltage lead from the tester to the fail side this time of the TVB2 box, and then again we can use Ohm's law to calculate the resulting current, and it comes out to be 10.3 milliamps. And if once the test is run and the measured leakage, if it comes out to be close to 10.3 milliamps, then we know the test is a true fail. One more thing to keep in mind is that the test should fail within 0.5 seconds of the dwell cycle. Remember, we set our dwell time to 1 second. So according to agency regulations, the test should fail within 0.5 second of the dwell cycle. If the test does not fail, then the unit is not properly reading leakage current, and should be repaired or calibrated. So this is one way of verifying, one very efficient and quick way of verifying if the Hipot tester portion of the tester is working within specs. Next, we're gonna review what ground bond or ground continuity test is. Well, again, if you guys can recall from our previous webinars, ground bond or ground continuity test is used to analyze the integrity of the safety ground on an electrical device. The safety ground needs to be able to handle any fault current that could be imposed upon it due to a product or installation failure. Therefore, a low impedance path to ground will allow the circuit protection device such as say fuses or circuit breakers on the input react immediately to protect the user from dangerous electrical shock. In order for the system of protection to effectively operate, there must be continuity, and continuity between conductive components and the product's ground pin or the ground terminal. What the ground bond tester does is that during the test, the ground bond tester injects current into the ground pin of a product and looks for a return path on the chassis or the exposed dead metal. Simultaneously, the instrument will measure the voltage drop across the safety ground circuit to calculate the impedance of the circuit. So here, essentially, what's going on is that high current, which is basically in the range of 10 to 30 amps based on agency standards, is being pumped through the ground pin of a device, and the instrument is measuring the voltage drop across the safety ground circuit to calculate the impedance of the circuit. So the result of a ground bond test is basically an impedance, and a general common ground bond test parameters are for a current of 10 to 30 amps with a maximum impedance of 100 to 200 milliohms. As you can see, this is a very small number, and we want this impedance value to be small in order for the ground circuit of a device to get rid of all the fault currents that may develop in the product. Okay. Again, as a reminder, please feel free to use our chat facility. Dwayne Davis will be more than happy to answer any questions regarding the material that is being presented today. Okay, now we just went over the ground bond test. It was more like a review of ground bond test. Next, we're going to get into the verification of ground bond. How do we verify whether our ground bond tester is measuring true passes and failures? So, again, for example, we're going to use the example of the TVB toolbox that we discussed earlier, and we're going to use the same table of resistance values and test settings. And as we know, just like for the voltage withstand test, we can have, there's a pass and fail terminal on the box for the ground bond test as well. So what we're going to do is, as an example, the ground bond test current that we're going to pick is will be 25 amps AC. If you refer back to that table, the failed circuit, the failed terminal on the ground-bound portion of the box includes a 200 milliohm resistor, and the pass circuit utilizes a 50 milliohm resistor. So the ground-bound unit would then be set for two separate tests, just like the Hipot test, a pass and a fail. The first test is a pass test. What we're going to do here is that this can be done by setting the ground-bound unit to a current of 25 amps AC. We can set and this is right out of that table again, and you guys will be able to access a copy of this presentation, so you can have that table. You can look at that table later on again. So the ground-bound unit will be set at 25 amps AC, a high limit of 100 milliohms, and a 1 second ramp-up time and a 1 second dwell time. The high current lead for this pass test, remember first we're verifying the pass side. So the pass test lead, the high current lead from the ground-bound unit is connected to the pass terminal on the ground-bound portion of the TVB2 box, and the return lead is connected to the return terminal of the TVB2 box and going back into the ground-bound tester. When the test is run, the resistance should measure around 50 milliohms, which should result in a pass. Next, to verify, to perform the fail test with the ground-bound unit, we're going to leave all the parameters the same as for the pass test. This time, what we're going to do is we're going to connect the high current lead. It's going to be moved from the it's going to be moved from the pass to the fail terminal on the TVB2 box. Similarly, when the test is run, the resistance should be around 200 milliohms, which again should result in an immediate test failure. And this is what we're verifying. We're verifying if the tester will fail correctly, and if it does, then we know that our ground-bound tester is working within specs. Again, it is important to remember that in specification with the agency regulations, the test should fail within 0.5 seconds of the dwell cycle. Remember here we set our dwell time to 1 second, and we should expect the test to fail within 0.5 seconds of the dwell cycle. If the test does not fail, the unit is not properly reading the resistance values and should be analyzed and checked for faults or defects. So that concludes our ground-bound test verification. Next, we're going to go over insulation resistance test. Well, again, if you did attend our previous webinars, our series of webinars in 2013, you should be decently aware of what insulation resistance test is and what it essentially does. So basically, while the insulation resistance is basically the most least commonly specified electrical safety test, but it can provide us with some valuable data. Similar to Hipot test, the insulation resistance test is run by shorting the mains inputs of a device under test. So whereas a Hipot test provides a leakage current value. Remember how we stress the insulation of the DUT in a Hipot test and measure the resulting leakage? Similarly, the insulation resistance test, what this does is it actually gives us a resistance measurement of the insulation itself. The insulation resistance test potential is generally specified by the safety agencies at 500 volts DC or 1000 volts DC. Now remember, compared to the Hipot test, there was a formula that we used to get the voltage for the Hipot test. Here, the agencies have specified the voltage for the insulation resistance test as 500 or 1000 volts DC. Now, since the test potential is DC in nature, once the capacitive portion of the insulation has charged, the only leakage current flowing through the insulation of our DUT is resistive in nature, and thus it allows the user to measure an insulation resistance value, which is why the name insulation resistance comes in. For short, we can call this test IR. Now, how is an insulation resistance test run? It is run in much the same way as a Hipot test. Basically, a high potential is applied to the current carrying conductors of the device under test, and the return point of this circuit is connected to the chassis. For example, we can think of running a IR test on solar panels, which involves shorting the positive and the negative terminals to high voltage and applying the return point to the metal frame. This way, the insulation is stressed, and the IR tester measures the leakage current on the exposed metal chassis. Then the IR tests are usually specified as a test for repaired equipment just after electrical devices have been repaired. It is a good practice to run an insulation resistance test, and it will give us some good quantitative data about how the repairs were. So, having reviewed or refreshed our minds with the insulation resistance test, we're going to get into how the IR test can be verified. So basically, how can we verify if our IR tester is working within specs? Well, similar to the other two Hipot test and the ground bond test, we're going to use the same example of our TVB2 box, a verification box, and the table. We're going to refer back to that same table with the resistor and settings. If you look at that table, the IR test voltage for this example, we can start with 500 volts DC. The fail circuit, if you look at the box, includes a 4 mega ohm resistor, and the pass circuit utilizes a 1 mega ohm resistor. The IR unit would then be set for, again, like the previous test, we'll have a pass test and a fail test. The first test will be a pass test. The IR unit is set at 500 volts DC. On the pass side, for the pass test, we're going to set a low limit of 2 mega ohms, a 2-second ramp up time, and a 1-second dwell time. So this time, the high voltage lead from the IR tester will be connected to the pass terminal of the IR portion on the TVB2 box, and the return lead again will be connected to the return terminal of the TVB2 box, going back to the unit's return port. When the test is run, the resistance value should be around 1 mega ohms. Remember, this is for the pass side, and the pass side is utilizing a resistor of 1 mega ohms. So if the result of the test is around or close to 1 mega ohm, this would result in a test pass. Similarly, the next test would be a fail test with the IR unit set to the same parameters as the pass test. This time the only difference would be that the high voltage lead will be moved from the fail terminal to the fail terminal on the IR portion of the TVB2 box. When the test is run, the resistance should be around 4 mega ohms. Remember, the fail side is utilizing a 4 mega ohm resistor, and if this is what the unit will read, anything close to 4 mega ohms, we know that it is a genuine fail, an immediate fail. Again, just like the previous two tests we discussed, based on specifications with the agency regulations, this test should again fail within 0.5 seconds of the dwell cycle. If it does not fail, the unit is not properly reading the leakage current and should be analyzed. Okay, so that covers our insulation resistance verification part. Next, we're going to get into line leakage test. We're going to briefly review what line leakage test is, and then we're going to go into how line leakage test can be tester can be verified. Now, from what we remember, the line leakage test, just like the Hipot test, it measures the current flowing through or on the surface of the insulation on a device under test. However, the line leakage test differs in that this measurement is performed while the product is running at the rated voltage, or at a high line condition of 110% of rated voltage. This is specified by some medical safety standards by UL, like 60601-1, where line leakage tests should be run at a high line condition. Anyways, the other major difference that is that how the leakage current is measured. Remember, for a Hipot test, the leakage current is measured through using a current sensing resistor on the return side of the circuit. Here, during a line leakage test, the current is measured through what is known as a measuring device, or MD for short. What an MD is basically, MDs are designed to simulate the impedance of the human body. Another aspect of the line leakage test that sets it apart from other electrical safety tests is the fact that it incorporates fault conditions. What are fault conditions? These fault conditions are designed to simulate the worst case scenarios that could happen during the instrument's operation. Three most common fault conditions are the opening of the neutral circuit, the reversal of the line polarity, and the opening of the ground circuit. Again, the idea behind running tests under these various configurations is to measure exactly how much leakage current a human could be exposed to while the product is running and subjected to a series of fault scenarios. If the leakage current value is sufficiently low enough under all such fault conditions, the product should be fine, or should be able to operate normally throughout its life cycle without really posing a shock hazard. Line leakage test parameters like other test parameters, they also vary greatly from one standard to another. However, some of the most commonly run line leakage tests are for compliance to the 60601-1 third edition standard, which is called the medical device standard, which is the medical device standard. For this standard, the line leakage test must be run at 110% of line voltage, and utilizing all the MDs. The acceptable leakage current values this is again based right out of the standard, range from 10 microamps all the way up to 10 milliamps. So there's a big gap there. Next, having gone over, refreshed ourselves with what line leakage test does, we're gonna look into how to verify if the line leakage test is working correctly. Well, line leakage verification is not as well defined as the verification for other test types. So we don't, we don't have a method, or I mean, we can use the TVB2 box, something similar to the TVB2 box, but the TVB2 box that we have currently does not contain terminals to test for the line leakage values. However, the same concept can be carried over to ensure that a line leakage unit is operating within the specified values. Since a product is operating at rated voltage while running a line leakage test, or 110% of rated voltage, most line leakage testers utilize a universal power receptacle, as shown in this picture. As a result, a simple fixture can be made to mate with the receptacle box. Basically, a standard plug terminating in two separate resistor values is the most simple means of creating a line leakage verification test fixture. Now we know that the leakage meter for the line leakage test reads between ground and neutral for normal polarity, and it reads between ground and line under reverse polarity. So separate resistors can be wired between line and ground, neutral and ground. So for example, for line leakage verification, a plug is wired with a 2 mega ohm resistor between line and ground, and a 200 kilo ohm resistor between neutral and ground. The first line leakage test is set to 120 volts AC, 60 hertz, with a high limit of 50 microamps, and reverse polarity, 5-second dwell time. Now these numbers are just being used as an example. These could change very well based on different standards. Now with the 2 mega ohm resistor from line to ground, the leakage current value should read about 60 microamps. Using Ohm's law, we can find what this current should be, and comes out to be 60 microamps. Now this leakage current should produce a failure on the test. We can run another test, a second test, which would check for a failure under normal polarity conditions. Again, we'll leave the same parameters, but this time we're going to set our high limit to 550 microamps. Normal polarity, again, this time we're utilizing a 200 kilo ohm resistor, which is wired from neutral to ground. Remember, we're testing reverse polarity, so the resistor, the 200 k ohm resistor, is wired from neutral to ground. The leakage current value should read, again based on Ohm's law, the current should read about 600 microamps, thus producing a failure on the test. While a line leakage tester can also uh, uh, it also contains various other relays. The main idea here is to show that the leakage detectors on the instrument fail in the presence of excessive leakage. That is the most important thing to verify here, is that if the detectors on the leakage tester are failing in the presence of excessive leakage current. If the two tests that we just discussed for verification test for line leakage, they they basically prove that if a line leakage meter is properly, whether a line leakage meter is properly reading leakage values or not. Okay, so this far we have we're nearing the end of our webinar today. We've covered what verification is, why is it important. We've given some examples from the standards, and then we've covered the basic electrical safety tests and how each of them can be verified. We've given examples of the test verification box. Next, I think all we're left here is with the summary of what we learned today. So basically, we went over the verification of electrical safety tester, and we know that it is critical in order to make sure that the tester is producing true fails and passes. If the safety tester is defective, it could lead to major issues such as shock hazards and eventually product recalls, and we don't want that. As a company, nobody wants their products to be recalled because of defects that were not detected prior to the product being sold. Performing regular verification ensures that all equipment is working within agency specifications. We know all the agencies, they emphasize very strongly on verification tests, but most importantly, verification plays a big role in ensuring user safety by differentiating between defective products and good products. Now, with the advent of microprocessor technology on electrical safety testing units, setting up instruments for test verification has become increasingly complex. Basically, electrical safety testing instruments now contain built-in suppressors that are basically designed to protect the unit circuitry. At the same time, damage to such suppressors can cause false readings on an instrument. So, taking simple steps to run daily verifications can spare a great deal of trouble and effort down the road, and it can also help avoid costly redesigns or product recalls. Using a resistor in series with the output of an electrical safety testing instrument will assist in validating measurements and ensuring that the failure detectors are functioning properly. Also, setting up a fixture with the, how we discussed, with the series of resistors, just like the TVB2 box, with calibrated resistor values, takes the verification process one step further. And additionally, we know that the microprocessor controlled safety testing devices, they also allow for programming and saving verification procedures. Such procedures can be set up to include working instructions and data acquisition as well. Verification methodology basically gives the operator a simple means of storing the verification test procedure as well as running validations on a daily basis. So performing regular verification basically ensures that all equipment is working within the agency specifications. Okay, at this time, I think we are um, finished with the presentation. Uh, we will leave the last few minutes for any questions and the questions that you guys might have. Once again, I would like to thank you all for your patience and for attending this very important webinar on electrical safety tester verification. I would also like to thank Jim for hosting this and Dwayne for assisting in any questions. If you would like to have a copy of this presentation, please again send an email to Jim, jimk@asresearch.com. You can reach us at 847-367-4077. Again, my name is Syed Abidi, and I'm the applications engineer here, and also your host, also your presenter for today's webinar. And having said that, again, thank you all for attending, and we're going to leave the session open for any questions that you guys might have. Thank you.
So I had one quick question here.
Yeah.
How important is it to make sure that you are including all of your test leads and everything else, and maybe any fixtures in your measurement when you're performing this verification?
Yes, of course, it is very important to when you're performing your verification, essentially. Going back to the example of the test verification box, it is always a good idea to take into account any lead resistance on any offsets. Make sure to take care of any offsets. And yeah, it is a very important thing to take into account all the leads and all the connections for verifying all the different test types.
Okay, one quick comment there on one of your last slides. I think you had a typo on one of your resistance values with the on the line leakage test, 120 k ohm with the 200k, or 120 volt with 200k. Should have been 600 microamps rather than 60.
Okay. Yeah, that's correct.
Okay.
Should have noticed that.
Okay. Yeah. So, if we want to send out copies on this, we might want to.
I'll make sure Jim has it corrected. Yep.
Okay. Other than that, very good job. Thank you.
Thank you.